So in the last lecture, we have introduced a new topology on the space of continuous functions from x to y, which was the topology of compact convergence. So now we will consider the relation between equicontinuous subsets of the space of continuous functions and this topology. And just to recall from the last lecture, recall that the topology of compact convergence is in general finer than the topology of pointwise convergence. This we saw in the last lecture, pointwise convergence. And now we shall prove that they coincide. So when you consider equicontinuous subsets of the continuous functions, then these two topologies coincide. So this is our next lemma. So lemma, or rather I should put it as a theorem. Theorem 2.1. So this theorem says that if, let's say, f is a subset of the space of continuous functions from x to y. So here again we assume that x is a general topological space and y is a metric space. So the topology of compact convergence can be defined on the continuous functions from x to y. And now we consider a subset f of this space which is equicontinuous. Then the subspace topology on f with respect to the topology of pointwise convergence on cxy and the topology of compact convergence on cxy are the same, meaning that we already know that the topology of pointwise convergence is coarser than the topology of compact convergence, but in this case when you give the subspace topology on f from the topology of pointwise convergence and then from the topology of compact convergence, then they give you the same topology on f. So let's try to prove this theorem, and we will use it in the proof of the Arzela-Ascoli theorem as well. So let's see a proof. So for the proof, we note that it is sufficient to prove that the subspace topology on f with respect to the topology of compact convergence is coarser than the subspace topology on f with respect to the topology of pointwise convergence, because we already know that the topology of compact convergence is in general finer than the topology of pointwise convergence. So what we want to prove here is the reverse inclusion. So the topology of pointwise convergence is coarser than the subspace topology with respect to the topology of pointwise convergence. So to show this, we will show the following. So let f be an element of f and BC f epsilon be a basis element in the topology of compact convergence, containing F, of course, containing F. Now what we want to show here is that there exists a basis element of the form BF F epsilon. So remember from the last lecture that these kinds of basis elements, when F is a finite set, gives you the topology of pointwise convergence. So here, of course, C, let me write here, is that C is compact in this notation and epsilon is greater than 0. And here in this notation, F is finite, and of course epsilon is the same. So there is a basis element BF F epsilon in the topology of pointwise convergence, such that we have F belongs to BF F epsilon, and because we are considering the subspace topology, we have to take the intersection with F, and this is a subset of BC F epsilon intersection with F. So this is what we want to show. Here, and for this we will use the fact that F is equicontinuous. So since for the given epsilon greater than 0, since F is equicontinuous, for each x in X, there exists a neighborhood. So I'm just using the definition of equicontinuous now. So there exists a neighborhood ux, this is a subset of x, such that we have that the distance between fx and fx prime is less than epsilon for all x prime belonging to ux and for all f in this set of functions f. So this is precisely the definition of equicontinuity. Now since we have chosen C to be a compact subset of X, since C is compact, so there exists a finite subcover from this open cover. So by the way, this UX's form an open cover. So there exists a finite set of neighborhoods ux1, ux2 and so on, let's say uxn, such that the subset C is contained inside the union of these uxi's I equal to 1 to n, and so therefore we can choose this finite set F to be our set of points that we have found here, x1, x2, xn, and now I claim that this is my required F. So now I claim that BF F epsilon intersection F is a subset of BC F epsilon intersection F, and this is what we wanted to show above. So this was our required statement. So it suffices to show that for this finite set F we have this inclusion. So let H belong to BF F epsilon intersection F, and we will show that H belongs to the right hand side set. So here let me make a slight modification. So rather than taking epsilon, I should take epsilon by 4, and the reason will become clear later. So this is epsilon by 4 here. Okay, this is also epsilon by 4, and with this epsilon by 4 neighborhood of f in the topology of pointwise convergence, then we will show this claim. Okay, so what happens, since H belongs to this set BF f epsilon by 4 intersection f, so this implies that the supremum over x belonging to f, the distance between fx and hx is less than epsilon by 4, and this is the same as saying that the supremum, rather the distance between fxi hxi is less than epsilon by 4 for all xi for all I in this set 1 to n. So for all I in this set 1 to up to n, and so we will use this for proving that our H actually belongs to the set BC f epsilon intersection f. So to show that H belongs to BC f epsilon intersection f, this is the same as saying that the supremum over x in C df x hx is less than epsilon, right? So this is what we have to show, and now we are going to break this kind of distance using the triangle inequality in 3 parts, as we have done many times before. So note that by the triangle inequality, we have that d of fx, so this is for any x in C, d of fx hx is less than or equal to, so first we have d of fx fxi plus d of fxi hxi plus d of hxi hx. So now we can again do the following. So 1, let's write this as 2, and let's have the middle term as 3. So the middle term C is less than epsilon by 4 because of this. So because of this star relation, so 3 is less than epsilon by 4 from this star, right? On the other hand, what we are left with is to show that both 1 and 2 are less than, sorry, this should be epsilon by 4, not 3 by 4, epsilon by 4, both are less than epsilon by 4 as well. And for this we will use the fact that we have chosen our neighborhoods such that d of fx prime is less than epsilon by 4 for all x prime in ux and for all f in f. So this is important. So we can plug in once f and once h and take x equal to xi and x prime equal to x. So this is what we are going to show. So to show that both 1 and 3 and 2 are less than epsilon by 4, we use the fact that for all x in uxi, okay, we have that d of fxi is less than epsilon by 4. So for all f in f, okay, so our neighborhoods were chosen such that this happens. Rather, I should write here g just to distinguish it from the already chosen function f. So in particular we have for g equal to f or g equal to h, that d of fxi is less than epsilon by 4, and d of hxi is also less than epsilon by 4, and this is precisely the first. So given x in C, we choose I such that x belongs to uxi, and then we have that the distance between fx and hx is less than or equal to 3 epsilon by 4 by our estimates here. So this is the first two terms, and this is the third term here, and all of them are less than epsilon by 4. So in fact there is a strict inequality here. This is strictly less than epsilon by 4, and this implies that the supremum over x in C, fx hx, is less than or equal to 3 epsilon by 4, because we are taking the supremum, but then this is strictly less than epsilon. So this means that h belongs to BC f epsilon intersection with f. So here we are using the fact that h belongs to both f and h belong to f in these two estimates. So this proves that the topology of compact convergence and the topology of pointwise convergence coincide on equicontinuous sets. So now with this theorem in hand, we are now ready to prove to give a sufficient condition for a subset of the space of continuous functions to be compact in the topology of compact convergence. So we will give this as a theorem, and let's see the statement of this theorem. So this is the statement of the theorem that we want. So here again, f is a subset of the space of continuous functions. Again, x is a general topological space and y is a metric space, and we are assuming f to be an equicontinuous subset. Okay, and we have a further assumption, which is that for each a in x, the following set fa. So this is a definition of the set fa, and this is just the set of points in y given by evaluating all the functions we have in f at the chosen point a. So you fix a and take every function in this set f, say small f, and you take f of a, and this gives you a set of points in y, and this set we call f of a. So this is a subset of y, and we assume that this has compact closure. Okay, so fa closure is compact in y. Then the closure of f in cxy is compact in the topology of compact convergence. So this is a sufficient condition for a subset of cxy to be compact in the topology of compact convergence, and in fact this is one part of the Arzelà-Ascoli theorem. So this is the forward implication, and the Arzela-Ascoli theorem itself, as I have mentioned before, which gives a characterization of compact sets in CXY in the topology of compact convergence. So this theorem 2.2 is just proving one way, which is that given a couple of conditions, then a set is compact. And in fact, this will be an if and only if statement, but we have to assume some extra conditions on our domain space X, and we will see that later. But first, let us try to prove this theorem using our previous theorem 2.1.